So last time, let's consider the integral from 0 to 2 of x squared plus 1 dx. 0 and 2 are called the limits of integration. They're just telling us the domain over which we're looking, or if you want to think about it in terms of rectangles, we're looking at the area of all of the rectangles from 0 to 2, whose heights are varying. Now, in order to do this, it's very similar to an indefinite integral. This is definite because we have limits of integration. I know the integral of x squared is 1/3 x cubed. Right? I'm just reversing the derivative process. And the integral of 1 is x. And because I have limits of integration, I don't need c. Right? The limits of integration force me into a specific type of thing. And now I'm just going to substitute. It will always be what I get when I substitute the upper limit of integration in. So in this case, 1/3 times 2 cubed plus 2 minus what I get when I substitute in the lower limit of integration. So in this case, 1/3 times 0 cubed plus 0. When I do this and simplify, 2 cubed is 8, so this will be 8/3 plus 6/3, which is 14/3. Right. So we've calculated the definite integral. A couple of facts that are important. This corresponds to the area under the curve. Right? It's related to it, but it isn't always the area. So something graphically, what we just found out is that if we took our curve x squared plus 1 from here to there, from 0 to 2, we found that this area from the curve to the x-axis has a value of 14/3. Right, that's the area there. Now, something to recognize, that this is above the x-axis. And we could consider a reflection of this. So let's look at negative x squared minus 1. So this is the quadratic that's here. It goes in this direction. And you'd think that you should get the same thing, but let's look at the integral from 0 to 2. I'm going to distribute the negative in, so negative x squared minus 1 dx. When I integrate negative x squared, I get negative 1/3 x cubed. When I integrate negative 1, I get negative x from 0 to 2. And some of you can already see what's going to happen. This will be negative 8/3 minus 2 minus 0 minus 0, and this is negative 14/3. So notice that I get a negative value for the space here because it's below the x-axis. Right? So although that does correspond to the area when you integrate, the portions that are above the x-axis are positive, and the portions that are below the x-axis will be negative. And that's an important distinction. Right? And it's related to ideas of change and type of change. A couple other facts. If you were to integrate from some value to itself, of a function, it's always equal to 0. Another thing that's important is if you were to integrate from b to a function, you will get the opposite of what you would get if you integrated in the from a to b. So this is a direction issue. So that's how those things are related. A couple other things I'd like to add. That if you have a constant times a function, and you're integrating that from a to b, that's the same thing as if you were to take the constant out and just integrate the function. Or to relate it to things we've already done, or to relate it to something, if you saw, I don't know, 2x squared plus 4, and you were integrating that from, I don't know, 0 to 1, you could factor the 2 out and just integrate x squared plus 2, and then multiply that that area by 2, or that value by 2, and you'll get the same thing. Last thing is that if a is less than or equal to c is less than or equal to b, so if c is between a and b, the integral from a to b of a function is equal to the integral from a to c of the function plus the integral from c to b of the function. So you can break it up into different intervals if you like.